Alright, this is the Chapter 17 homework for dynamics. Been a while since I answered some of these questions, so I'm gonna kind of read through the questions as I do it to remember, what we're solving for and what exactly I'm doing. So the first question, pretty straightforward, has to do with the flywheel rotating a certain speed. And each time a hole is punched, it's gonna slow down the rotation. Energy is going to be taken out of the system. So we know we're going to use work for this one. First thing I did, convert the 300 rotations per minute to rads a second, and then we're just going to use the conservation of energy equation. So we have the kinetic energy in the beginning, work from 1 to 2, and the kinetic energy after. So in this case, the kinetic energy is going to be 1/2 mass moment of inertia times the angular velocity. Since it's only rotating, it's not translating at all, and it actually gives us the moment, the work done after each hole punch, which is 1,800 feet-pounds. And like I mentioned before, we know it tells us that roughly 10% is lost every time a hole is punched. So we know that this is going to be taken out of the system. And using this information, you can actually solve for the mass moment of inertia from the equation. And then from there, you can actually just use the work done as a moment because it's slowing the rotation down. So it's causing a moment in the opposite direction. And we know that a moment is just, or the work done by a moment is just the moment times how far it rotates theta. And you can, so part B, it gives you the moment, which is 25 in the question. So it gives you the moment. So you can basically just solve for the total amount of rotations by dividing, the work done by the moment given. And that will give you the amount of, the total angle in radians. If you just divide that by 2 pi, you get the total rotations because, one rotation is 2 pi. So pretty straightforward. So this one is the bar, and it's released from rest, and we're pretty much going to calculate the angular velocity when it is vertical, and then we're also going to solve for it with the weight and length when it's given to us. So pretty much you just want to solve it symbolically and then plug everything in. Pretty straightforward. So to solve for it symbolically, we're gonna have the same equation. So the work done from moving from position 1 to 2 is going to equal the kinetic energy at the end. And it says it starts from rest, so we know that this is going to be 0. So we know that the what's the word I'm looking for? The potential energy is going to be mass gravity times height. So the work done is going to be, that change in height essentially. So it's moving half of the radius because the center of mass of the bar is at the middle. So that's where like the weight force is acting on. And then we know that's going to equal the kinetic energy at the end. So in this case, we have translation. The bar is actually moving down. And there's also rotation because it's around a fixed point at A. So we know that it's going to have 2 parts for the kinetic equation. We also know that velocity rotating around a fixed point is going to equal the angular velocity times the radius. So since we're just using the middle of the bar where the weight vector would be, we can actually just use WL over 2. So that's all going to be squared. And then for a bar moving at the end, a bar moving, at the end is 1 over 12. Times 2 is going to be 1 over 24. Times 1/2, I should say. And you can actually just eliminate the L squared by dividing it to the other side. And you can combine the two angular velocities squared and solve for the angular velocity that way. So if it gives us the length, we can actually just solve for the angular velocity that way. And then for the reaction, we actually are just going to use the kinetic equation, force equals mass times acceleration. So we know that the force at A, this is for the reaction at A, minus the weight, because the weight is essentially, pulling it down, is going to equal the mass times the acceleration. And we know the acceleration is r omega squared. So we can go ahead and switch that over to L over 2 omega squared, because we're using the radius at the halfway point. And that's going to give us this. So the reaction is 3 over 2 times the weight. And it gives us the two values, so we can actually just plug these in for the angular velocity equation we solved here, and the reaction at A equation here, and you can get the two numerical answers after we solve for it all symbolically. So, all right, so this one was the L shape. Pretty much the spring is released and it moves it up to where AB is 90 degrees. So this one was a little tricky to figure out, but what you have to do is you have to treat the x-axis as like the neutral point, where you're going to calculate the work done as it moves 1 to 2. So this lower one, actually I'll start with the upper one. So this upper one, it's moving, sine of 30 degrees upwards. And this one is moving, cosine of 30 upwards. So what you have to do is you have to treat one of these is negative and one of these is positive. So I treated this one as like a negative. I think I plugged in the equation as a negative length. So pretty much you just write out the conservation of energy equation. So kinetic plus potential equals final kinetic plus potential. But we know the kinetic at the end is going to be 0 because it says its maximum is 90 degrees. So it stops moving once it gets to 90 degrees. For the initial kinetic energy, we're going to have just rotation. And that can be written as 1/2 mass mode of inertia times the angular velocity squared. And when you sub in I, which is 1/3 ml square for this shape, you get that. And for the initial potential energy, essentially it's going to be, sorry, I forgot to preface this. So since it doesn't give us any initial information about the original, you actually use the conservation of energy for when it's 30 degrees versus to when it's 90 degrees. So this is the potential energy when it's at 30 degrees. Gives us this right here. And this is where I was saying that you have to treat this one as a negative because it's moving, you have to treat the x-axis as like the point to which both are moving from. So this one's moving away from the x-axis and this one's actually moving towards the x-axis. So I just treated this as like a negative length So when you plug it in, it's actually going to end up being, the top bar, which is the sine of 30, however it's moving, and then this one is going to be the negative cosine 30 for this bar, or as far as how far it's moving relative to the length. So yeah, you can just do some algebra from here, plug everything into this equation. So we now have T3, T2, V2, and V3. So you can plug everything in and solve for the angular velocity, which gives us 7.09 rads a second. So yeah, you pretty much just solve for all these individual, put it all together, and then just do all of the algebra, solve for it that way. So pretty straightforward. Okay, so this one was the wheel rotating. So this one is actually simpler than I expected, because the moment couple applied to the wrench right here actually creates the same exact moment on the tire itself, which may not be intuitive, but it actually makes sense if you think about it. Initially, it may not be intuitive because you actually don't have to consider the distance between the two moments. So pretty much we know a couple moment is force times distance between the two couple forces. So we can just solve for the moment that way. And it gives us the radius of gyration, so we can actually solve for the mass moment of inertia. And it also gives us the time, because the problem tells us that the couple is applied for 0.1 seconds. And you can actually just plug it into the momentum equation for moments. So it's mass moment of inertia times angular velocity plus the sum of the moments times time equals the final mass moment of inertia times the final angular velocity. So you can actually just plug these all in straightforward and solve for the angular velocity that way. So yeah, we have the moment. We know it's not rotating to start. It's going to equal I, which we solve for, times the angular velocity, and you can just solve for it that way. Pretty simple. All right, so this one is the so the sphere, and let's see. So it has an initial velocity, but it's has an angular velocity in the other direction. So that means it's not there is slip occurring, which means that there's going to be a coefficient of static friction involved, because it's moving one direction, it's rotating, the opposite direction. So this one you have to do all symbolically. So we have the forces involved. So we have the momentum in the y direction, which it ultimately doesn't change at all in the y direction. So we know that n is going to equal the mass times gravity. Friction always is the coefficient times n. So force friction is mu k mg. And then for this one, we do it in the x direction as well, because we know that there's only the force friction acting on it as far as external forces in the x direction. So we can actually just plug everything in. So we know the mass times velocity in the x direction, which is v naught, and we know that the force from the friction is moving in the opposite direction, so it's actually taking momentum out of the system, and pretty much we're just going to find when it equals when it stops moving. So we know that the final momentum is going to be 0. So ultimately the initial momentum has to equal the momentum taken out by the friction force. And this gives us an equation right there. And then we're also going to do the same for the moments. So the sum of the moments times the time is going to equal the initial angular momentum the initial angular momentum plus the moment times time is going to equal the final angular momentum. Same thing, we know that the final angular momentum is 0, and we know that the moment from the friction equals the force friction times the radius, because it's acting, the radius away from the center. So that gives us another equation. Get some canceling here, we're able to solve for the initial angular velocity that way. And then finally, we can plug in the this force equation into this one to solve for the time relative to the initial velocity, gravity, and the coefficient of static friction or kinetic friction. So yeah, pretty much just solving for a couple different equations, different iterations of the same, just using different variables. So, all right. And for 6, so this one was the one with this part basically comes down when it's rotating, and you're supposed to find the change in angular velocity, essentially. It doesn't give us any measurements or anything, so we know that it's going to be symbolic. How we go about solving this is the key here is the mass moment of inertia is different depending on the orientation of the sphere relative to the axis of rotation. So as you can see here, this is like this base plate. It's rotating about the center of gravity, very center of the circle, rotating that way. So we know the mass moment of inertia for that is 1/2 mr squared. If it's rotating about one of the axes, like this one is, because this one, when it rotates this way, it's rotating about like the center axis instead of the actual, center of the circle. So the mass moment of inertia for that is 1/4 mr squared. And pretty much we can just plug all these into our moment conservation of momentum equation. So we know that there's no external moment occurring. The only thing that's changing is going to be the mass moment of inertia. So we can plug all these in. So we have the mass moment of inertia for the bottom circle and then the top circle, but it's only a half circle, so you can actually just half the mass in this case. And then for the final, exact same thing. I'm going to half the mass, but I know that this falls down and becomes this angular momentum because it's now rotating about the very center dot instead of the, center axis in either the y direction. And most of this stuff is going to cancel. So really all we're going to have is the two different fractions from the mass moment of inertias. And you can actually just solve for the ratio that way. So we know that W naught is 5/6 of W2. So it speeds up slightly. All right, and then I did these last two in opposite order by accident, so this is number 8. This one took me a little while to figure out, kind of complicated. There's just a lot more going on here than you may expect. So we have, a person jumping down onto a board like a gymnast, and it launches this person up in the air. But there's a couple things we have to consider. It doesn't give us like a force, right? So we don't know the exact force being applied to a board. We only have how high the person is jumping from in their mass. So we know we can get a force from that, but that's going to be key number 1. Key number 2 is the board also has mass, and it's given to us in the problem, 15 kilograms. So essentially we're going to have to account for the actual rotation of the board. And one of the things you have to consider for this problem as well is when
there's a brief moment when the person hits this board rotates, and this person starts moving up. They're all going to be moving the same speed, and that speed, the velocity, is going to be the angular velocity times the radius for these people. It's, the angular velocity of the board, and this person's going to be moving the same speed. The angular velocity times radius. You think about it, they're all connected to the board at the same time when the board is moving. So that's kind of the idea behind it. So I set this equation up as we have the momentum of the first person before he hits the board. So this is the initial momentum before he hits the board. That's going to equal the momentum of the board rotating from rotation. So that one's going to have an angular velocity. And then we're also going to have the momentum of the first person who jumped and the second person who is now moving upward. And for the velocity, we can actually solve for it using the conservation of energy, or converting kinetic energy to potential energy. So you can solve for V that way. So I just plug in 2gh, the square root of 2gh. And then for this one, the length of the board is actually 2L, and you have to square that. So that's going to give you L squared over 4 divided by 12 is 1/3. And the final one, we know the velocity is going to be the same. And it's going to equal both of their masses because they're both moving the same speed. So here we have L over omega. And like I mentioned before, that's actually going to equal the velocity of V2. Both of these people are moving at the ends. So you can actually convert this LW to V2 and solve for V2 that way. So, yep, that's how you solve for the velocity. And then you can just convert this velocity into height using a reverse of the conversion that we used earlier. And you can just find the height that way because you know the acceleration of gravity as well as the velocity that the person is moving. So that's how you solve that one. Okay, so this one, number 8 or 7, sorry, this one's the bullet hitting the disc and it starts rotating. So the key for this one is the impact of the bullet is so fast that the time is essentially 0. So what we can do is we can solve for the it's a little interesting because we know ultimately the momentum is going to cause this to shift this way, but the bullet hitting is also going to cause like a rotation of some sort that's going to affect the end velocity of everything, and they may be in like 2 different directions. So it may, as soon as it hits, it may rotate in one direction, but the momentum of the bullet is pushing the actual device in another direction. So you have to solve for this essentially twice, so 2 iterations. So the first iteration is the bullet hits the ball or the disc, and it's going to push it in the right direction, but it's going to cause a moment in the other direction. And then the second time you have to solve it, it's the exact same thing, but it's after the amount of time that these two even out. So the rotation evens out, stops rotating or starts rotating in the other direction because the velocity, pushed it to start rotating in that direction. So you essentially have to solve for it twice. So the first time I just did the normal conservation of momentum in the x direction, and like I said, the time the bullet hits is so small that it essentially doesn't matter. So it's really just going to be the momentum of the bullet is going to equal the momentum of the disc itself. Which makes sense. I mean, the mass of the bullet is also small enough where you wouldn't have to really consider the mass of the bullet in the disc. Pretty much the same mass. So yeah, you can solve for the angular velocity that way. Or that gives you one equation. And the other equation is going to be the moments. Again, the moment caused by the force, which is force times distance times time, is going to be 0 because the time is so negligible. It doesn't really make a difference. So that's ultimately going to equal, how easily the disk rotates times the angular velocity. You can solve for the angular velocity that way. So now we have 2 equations here. And the final one, I'm going to do the same thing. But in this case, I'm going to use the rotation around like a point O, let's say, like a distance from the center, which is going to equal, the angular velocity of the center plus the mass times velocity times the distance, ultimately. Instead of just the rotation part, it's also going to have the translation part here. And we know this velocity equals the radius times the angular velocity. So we can just plug everything in here. We get some cancellation of the radiuses, or the radii, I should say, and you can solve for W2. And then the v squared equals omega times r. So you can actually go backwards on that. And you're just multiplying what we just found by another r, which cancels out the r on the bottom. So we know that, so we know that v2 equals mass times initial velocity divided by 3m. So